line spectra. So the line spectra of hydrogen provides evidence of this particle nature, right? The line spectra represents an emission or an absorption spectra consisting of isolated lines, right? So you all would have seen this in you all may have seen this in in chemistry. Hold on, I just want to see if I can huh? Yeah, same module we on. Hold on, I just want to show you how a line spectrum in. Let me just get it from here. Let's give me one step. My diagram not popping up. I don't know. Once you here. Once you here. Once you here, we go to. I'm just looking for my diagram, right? I had a diagram from here, but I'm not seeing it. Try this one. Right, can I zoom up a little bit again? Y'all see that? Yeah. All right. So forget your little arrows and thing, right? We just focusing on the different energy levels and the ground state. So for example, right? We all know from chemistry, see all these lines here? All these lines represent the energy levels where electrons can be found. Remember that? Can an electron be found anywhere in between? Ariane, can an electron be floating in the middle here? No. An electron has the oh wait, I can zoom in here, but I can't zoom in there. That's not I got it right. So we can't find an electron in the middle there. Electrons either on the ground state or here or here or here. All right. Suppose I want an electron, right? I want an electron to go from here to here. I wanted to go from NH2 to NH1. I wanted to go down to the ground state. What must happen? Right. For you to move from N2 Nikela all the way down to NH1, you have to lose, is it any amount of energy or a specific amount of energy? A specific amount of energy. So you have to lose a packet of energy. So what this line spectrum shows, it shows particle nature, right? It has to lose a particular packet or particular particle, okay? So the only way it can move from one energy to the next, it has to lose a particular amount of energy or gain a particular amount of energy. Are you okay with that? How do you just figure out how much energy it has to lose? Well, watch this here. This value here is minus 3.4 electron volts. And this value here is minus 13.6 electron volts. So the amount of energy it has to lose is simply minus 3.4 and then minus 13.6. How much is that? 10 points? This thing blocked. Anyway, 10.2 electron volts. I just convert electron volts to joules again. Multiply by 1.6 by 10 to the minus 90. Okay? So if you multiply by 1.6 by 10 to the minus 90, you can calculate the exact amount of energy it has to lose to go down to the ground state. Are you okay with that? So to go from one state to the next, you have to lose an exact amount of energy. Right? So again, what does this show? This shows particle nature of lines. Everybody okay with that? Sorry, I didn't multiply anything, sir. I just minus different energy level. So I minus the minus 3.4 and the minus 30.6. Okay, so I was just trying to show you how much energy it has to lose. Okay. Okay. Everybody okay with that? Online, you all okay with that? Right, so that just to give you an idea of how these lines structure work, right? And if you know the joules, the energy, if you find out the wavelength that will be given off. Yeah. You're using what? E is equal to? What are you using? If you want to figure out the wavelength deviation. If you want to, sorry, HC on lambda. Nice, HC on lambda allows to find the wavelength. Very good. Very good. Right, so that's what I want you to learn from the line spectrum, right? Right. So before I move on to X-rays, right? You all recognize the things that show particle nature. What were the 4 things that we learned? 4 things that allowed us to show particle nature. Well, we know what wave nature, right? Wave nature was like what? Reflection, refraction, diffraction, interference, right? But what were the things that showed? What were the things that showed particle nature? Number 1 was what? That was what we started in module with. Let's see it. Photoelectric effects. Thanks, Nakela. What else? Millikan's all job. Huh? Somebody else. We did. No, that was Einstein. Einstein was the Broglie. The Broglie, right? Right? Remember the Broglie wavelength? Sorry, the Broglie wavelength. Yeah. And one more thing, showed particle nature. This email probably get out of line spectrum. Right? All of these showed particle nature of light. That's okay? Well, we know what showed wave particle wave, that's what you all studied in Form 5, right? And Unit 1 as well. All those things showed particle nature of light. Right? Now I want to take a look at X-rays. X-rays, the way they are produced are very similar to photoelectric effects. All right, hey, I wonder for simulation. I never look for a simulation, but that's a good idea. I would just look for a simulation on that. Yes. X-ray production, no, whatever simulation. I never did this. All right, let me see if this video out, right? I never did this before ever.
Production of X-rays. The lab setup shown here was designed by Coolidge, and hence it is called Coolidge tube. It contains a highly evacuated glass bulb containing a cathode, which is a tungsten filament, and anode, which is a target made up of metal of high atomic weight. The pressure inside the bulb is maintained at 10 to the power of -6 millimeters mercury. When the cathode is heated by passing a current through it from a low-tension battery, it emits cathode rays. These rays are nothing but electrons. The filament is surrounded by a molybdenum cylinder, which is kept at a negative potential to the filament. This repels the electrons further, and hence the electrons form a fine pencil beam at the center of the cylinder. This pencil beam is also accelerated by the cylinder towards the target. The target is made up of a copper block in which a piece of tungsten or molybdenum is fixed. High thermal conductivity is used to carry away the heat generated to the cooling setup. Here we use copper, which is a good conductor of heat and can take the heat away from the molybdenum metal towards the water cooling system. The target is also tilted at an angle of 45 degrees, causing the electrons to hit at an angle. This will produce the X-rays almost perpendicular to the electron beam. A very high potential of 20 kV is applied between the source and the target. Due to the high potential difference, the electrons are accelerated towards the anode and it hits the metal. When it hits, the kinetic energy is transferred to produce X-rays. The intensity of the X-rays depends on the number of electrons striking the metal target. So, if we can increase the rate of electrons emitted by the filament by increasing the current flowing through the filament, then we can increase the intensity of the X-rays.
That's it. That's basically, right? That's basically how, what's that? Right, so here's what is happened. Let me just see if it happens, right? You know have it, but you're seeing what's going on, right? You're seeing what's going on, right? Okay, nice. So let's see why the X-rays are produced. So that one thing. It was actually showing you how it was hitting. That's not right. I'm just get back one. So that one. No.
Hello and welcome to the video on X-rays. In this video, we will explore characteristic and continuous X-rays. X-rays are a form of electromagnetic
Let's see if it, not sure if this. Let's see if this is the
waves, just like visible light, radio waves, and microwaves. In the electromagnetic spectrum, X-rays have higher energy than visible light but lower energy than gamma rays, making them the second most energetic type of radiation in the spectrum. There are two main types of X-rays, characteristic X-rays and continuous X-rays. Characteristic X-rays are produced when high-energy electrons collide with atoms in a target material. These collisions knock out the inner shell electrons of their orbits, creating vacancies or holes in the inner shells. To fill these vacancies, electrons from outer shells jump in, and in the process, they release energy in the form of X-rays.
right, Devesh, tell me now, how we getting these X-rays? Yeah, huh? Well, what did we don't tell you? This man para that's deep. I never talk with this man para. But you're basically see there. So the electrons that came out from the anode, right? Those electrons hit the metal, remember the little metal at the angle, right? And it hits out the deep lying electrons. So what will happen now is the next electron wants to take its place. But we know to go from a high level to a low level, you have to give up energy, right? And that energy is in the form of X-rays. Are you okay with that? It's a real nice stimulation. It's not the video I watched last time, but I like it.
When an electron from the L shell jumps to the K shell, it emits a characteristic X-ray known as K-alpha. Similarly, transitions from the M and N shells result in K-beta and K-gamma X-rays, respectively. The probability of a transition from one shell to another depends on the proximity of the shells, so transitions from neighboring shells are more likely than transitions from farther away shells. The emitted wavelengths of these X-rays are unique to each element. Therefore, they are called characteristic X-rays because they serve as fingerprints for identifying the elements present in a sample. On the other hand, continuous X-rays have a continuous range of frequencies or energies. They are produced when high-energy electrons interact with target atoms, but instead of causing inner shell ionization, they are slowed down and deviated from their original paths by the nucleus of the target atoms. During this deceleration process, the electrons lose energy, and this energy loss is emitted as continuous X-rays. The energy of the emitted X-rays depends on the energy of the bombarding electrons, and by adjusting the energy of the electrons, you can obtain X-rays of different frequencies or energies. We hope you would have learned something new. Thanks for watching.
There's something new. The desimulation, so you can probably follow this guy. Who is this? These simulations are real bad. Chan Visual Physics 2023. That's probably why. But I didn't find this last day. This is something new. This is real. Right? You actually see how some of these things happen. Now, some of these things we can't reproduce in the lab. Right? So it's real nice how you can see these things, right? So Chan Visual Physics. Okay, you have to look at that. I'll show you plenty. Look, you have the photoelectric effect, you have diffraction weighting, you have plenty of show. Right, so look at follow it. All right, so if we go back to the notes now, the notes have basically the same thing, just diagrams, no nice simulation like that. So what it basically explained there is how the X-rays are produced and the two types of X-rays being produced, right? Right? So same thing here. You recognize that? Same diagram? Yeah? What is blue thing coming out there, Higash? The X-rays and the red thing. The electrons, right? And one of the things that's being produced a lot here in these experiments is what? Heat. So that's why they have those copper anodes, right? Pulling it out. Right? So right? So it's the same process, same thing we just going to run through. We have X-rays, X-ray production. In modern form of X-ray tube is shown below. A focused beam of electrons is accelerated towards the target. And what controls the acceleration of the electrons? The voltage. Right? So everybody okay with that? The current affects the intensity. Right? Remember the same thing we learned in photoelectric effects. Okay? Current affects the intensity. The potential difference affects the energy that the movement with. And if you control the energy, you control the speed. Okay? You all remember how to go from voltage to energy? Is equal to what? Voltage to energy. Is equal to? No. From if they're given voltage. How you go from voltage to energy? Is equal to? E is energy. QV. Voltage affects the speed of the electron. Current affects the number of electrons, basically. Okay? Voltage affects the speed of the electron or the energy of the electron. And the formula I gave you E is equal to QV is energy. So the modern form of X-ray tube is shown below. A focused beam of electrons is accelerated towards target during the half cycles positive with respect to the filament. On collisions, the electrons decelerate rapidly and X-rays are produced. Right? But here's the problem: 99% of the kinetic energy goes towards producing heat. Okay? The target has a high melting point, so it can handle all the heat. For example, tungsten or molybdenum embedded in copper rod. The purpose of the copper rod is to conduct heat away. The rod is cooled with oil. The one I showed you there, they use water to cool it down, right? True, which has cooling fans and thing, right? So, am I able to went for X-ray? Tell now the machines are right? And you have to cool the room as well, right? Because of how much heat it produces. The intensity of the X-rays, this is what you're talking about, right, Nikolai? The intensity of the X-ray beam increases with the number of electrons hitting the target, and therefore the filament current controls the intensity of the X-ray. It is also increased by increasing the PD, which increases the energy. Right, which the electrons hit the target, making more energy available for the X-ray production. Right, here's a small question. Calculate the wavelength of the most energetic X-rays produced by the tube. They give you the voltage. You have to remember that the most energetic X-rays are produced when the electrons lose, most important word there, all of the energy. Right, so I'll show you the working here. That's the formula. You multiply the charge by electron by the voltage, and you get the energy. So the most energetic X-rays will have that amount of energy. Okay, and if we know the energy, we can use HC on lambda, right? HC sulfur lambda, and we get that. Yes, sir. All these have constants, all the ticks are constants. Okay. Right, and so you will know if you answer right, the wavelength of X-ray is around that value. Right? If you get -7 or -8, something wrong. Because you get light. Yeah, you have to get in wavelength that in the spectrum for X-ray. Okay. Everybody okay with that? Okay, so it shows you how to get the wavelength, right? Online. You okay with that? So in module 3, all that's left for us to do is after we do X-rays, we have to do. Right? Or those time is the exact date for the exam, right? Right, well, tell me when the exam is, and I will set aside I know for one night that makes sense now. But we want to do like a whole day or a half day or something before you look exam, before you look exam. Right? Crazy quality, sometimes I'll put but I'll try and go through everything. I don't know where you're getting for exam, but I'll try and go through everything. Right now, what you can find out, what you're getting, tell them now, you're not tell them what we're doing. No, but what you can ask, I know, but you can't give you can tell them what topic is coming. Let's ask them, right? Ask them what. If you don't tell us, we can get it right in there. Right. Properties of X-rays, you know all this already. Travels in straight lines at the velocity of light. They cannot be deflected by electric or magnetic fields. They penetrate matter, and it's at least with materials of high density, they are reflected and diffracted and so on, right? But you can read up on that, right? Uses of X-rays, right? We just did the X-ray spectrum, right? Anybody can just re-explain it, right? Watch here. These are the characteristic X-rays. These are the continuous. Anybody remember? What produces the characteristic X-rays? No, what produces them? Right. When one of the electrons knock off a deep lying electron in the target material, and the next electron takes its place. Those are the characteristics. So those are the high peaks of them. But the continuous part is produced by right. When the electrons leave the filament and it goes to the nucleus, it loses some energy, right? Causing a little deflection in parts. And that energy that's being lost is within all these waveforms, the big wave shape. That's okay? So make sure you can draw it and explain it. All right? It's not us, the P and L and M. That's where she is. The main frequency, yeah, those will be a little more declined. So you will see those produce higher intensity. That's why you will see those spikes. So the frequency that feels that will be a little bit different. All right. Nice. We talked about that already. Right. One last thing is something called the X-ray absorption, right? That's the attenuation formula. Yes, recording. All right. I want to explain that attenuation thing, right? So what you're saying? What would happen, right? What would happen? So let's say Michaela break her hand, and let's say Aaron break his leg, right? Michaela. Right? So both of them to get the image, right? To get the image, we will need different intensities of the X-ray. So there's a formula that is to help control the intensity needed, right? So imagine this is this is the medium that you want to find the image of, right? Has a thickness X. And an intensity I naught. I just keep going. Right? So here's what will happen. There's an intensity that will come through here. But because of the material, so one might be a hand, one might be a foot, one might be like a skull or something. Right? Right? Every material has its own attenuation. Right? Attenuation means how much it will absorb. All right? And as a result of the intensity of the X-rays going through here, some of it is absorbed. And you'll get a certain amount I coming out. Right? So this I tells you the intensity that will come out of the material. So based on what you find in the X-ray of the bone, or if it's people use X-rays to find the thickness of a sheet of metal, based on what material you're using, you can figure out the intensity here required. All right? And the formula is I naught T mu X. You don't have this? Yeah, it did. Right? I naught is the incident intensity X-ray, X is thickness, and mu is attenuation. Yeah, it's there. Check out the X-ray absorption. Yeah. Check on the X-ray absorption. Huh? There's to find the intensity that comes out after it passes through the medium. I know to be total intensity. I know to be the highest intensity. Yeah. Which is give you like 3,000. I don't know about 3,000. Yeah, I use long here. Huh? Long? Yeah, you're turning me on. Yeah. Here's why you had to use long to be arguing. I'm gonna say the videos. So far they get that done. Which one? All like the math videos in the season. I am a cool. You know what? Yeah. Now we're talking about TikTok videos. Yeah. I math so in the season is good. I am a cool. Yeah. You know one. That's what? Log. Make sure log groups. Yeah. Anything that gonna. That's no Starbucks. That's one see which one kitchen and which one no. That one kitchen. Yeah. I surely that the best one I have is I have a group. No. Where are you going behind? Now record video. Probably going to sequence of the purpose. Sorry, not a single bit. No, where are we on? You want to go you know that? He was orange. So yeah, very very fun. Balance. Develop it and not so let's say more force. I'm gonna do it because about my parts. Yeah, no, that's proven right. Yeah, Mike. All right, but you get this? But you get this? But you have this? Right, so let's apply this now. Right? Alright, part of that question missing, right? Try this here. I think best I could do there. Oh wait, that is full screen? I don't know what yet. I just have all them cropped out now. But you make a mistake here, it's be N, right? You make a mistake here, right? This should be N. X to the N, right? Yeah, I think it's X to the N. No, when you make a mistake, it's X to the N. Oh yeah, try this please. Try this please. Right, sometimes X will come as a whole number 3, yeah? I know what that's the best not good. That's the most complicated again, but you again you will be not good. No, not it. That's full screen. That's full screen there, yeah. We do it part, we do the second part, right? I'll go over here to let's have them cropped out. Number right on there.
Press view on the
Huh?
press view on each top. Right hand side.
Yeah, no, the same thing.
Press the-
A Zoom presentation.
That's all, yeah. Carry that in.
Hi itself. Huh?
Wait, yeah, keep on.
Yeah, like everything right there.
So press control and then scroll this.
Come right in, boy.
Oh, okay. Okay, let's go. I want to know.
Yeah, absorption question is mute. Okay, get it. Yeah, do that again. Right?
Full of control and scroll.
Yeah, but it does.
Yeah,
Yeah, but it.
full of control and scroll.
I don't have anything.
Let's go to higher, go straight in.
Oh, okay. All right. You lost mine out. But everything you see in there, 3 marks and 4 marks. Everything. Everything there is college question, yeah. We do part 1, 2. Yeah, part 1, 2 with 3 marks. You're right, not some of them thing.
Any balcony.
Where? You back?
Oh shit, my God.
Yeah. Hey, pagkamu ko that's not. How you doing the first part? How you converting the wavelength to the electron volts? And then you find the E in joules and then convert the joules to electron volts, right? I work for that one time now. How about look at now? It's 6.64, right?
6.63.
By 10 to the minus. 3 by 10 to the 8. What's your wavelength? 10 to the minus 11. How much you all got? That's part we are doing first. By 10 to the minus. Right? That's the value in joules, right? And then divide by 1.6 by 10 to the minus 19. That'll be a value in electron volts. How much is that? 100 and? Alright. That's it wrong, but right, you can probably write doesn't mega electron volts. Well, I just find out about it. Can by being so big. Online to be sharp. Well, you got to pass P there. Okay, yeah, she got the same thing. 1, 2, yeah, she got the same thing. Kilo electron volts.
You know, say mega.
Whatever, she write it in kilo. Anyone could do
When I said 36, I want to say video. Very guys, it's not a kids.
Oh, yeah. Right, to the next part. Part C. Yeah, remember the absorption coefficient is mu, right? That's mu.
You can't just wait to that spectrum.
High up. Fly high up now. So watch, when you reach here, I think the move goes all out. When you reach here, you do integration by parts. So you do the usual thing, right? When you reach here, n equal to 1. They show left and right the same thing. N equal to k, n equal to k plus 1. K plus 1 is the progress, right? So when you break it up in integration by parts, C and break it up and simplify it. Right? So when you reach here, you gotta break it down. Huh? Press it positive 3 times. Yes. 1, 2, hold it a few seconds. 3, 4, go again. You hear something. Keep pressing till you hear something.
Not that one boy. Because you want to say you are good.
No, just keep pressing.
It's shit. Someone inside the office, next to his desk, and he was up.
I showed him man last week. It's still in the man asked man. Did that you Aryan?
Iron.
Asking the same thing last week. Huh? You only phone.
He realized this story, that point. No one again is first answer. Yeah. Hey, man,
Well, yeah, and you got it put up, we went down there.
hey, man, I'm a trade person.
Huh?
Wait, trade person.
And thing in class here?
Interesting, why? Yeah, I see it.
Are you ready? Right, so here's what they ask, right? The question asks you to, they give you the mu value, consider a case for hypothetical absorption coefficient and the wavelength using 6 part B. What thickness of material is required to attenuate the intensity to 1% of the incident intensity? It's something real complicated, right? But real simple. This is mu. The way to find thickness, which is x, no, the thickness would just be in centimeters. And then they want 1% of I naught. That makes sense? So they want the I value to be 1%. 1% is 0.01 I naught. Okay, so if I go to the formula, I is equal to I naught E minus mu x.
Yes, we have one.
Right, they want the I value to be 0.01 I naught.
I think that's one on the.
Is equal to I naught. E minus mu is 0.3 x. Right? But here's the problem, right? The problem is if you don't know about ln. Yeah, because I is 0.01 I naught. So that we have to cancel. Right? I is 0.01 of I naught. I give you a hard one too, sorry. So I give you an easy one. Right? The I naught will cancel. And here's where your little match to come in. You take log on both sides. How do I take that for you out? Right on that same spot. I will take log on both sides, right? So you'll get ln 0.01 is equal to ln E minus 0.3x. Right? Remember ln E cancel and you'll get ln 0.01 over.
Take it as pretty massive.
Which one?
Ready?
Right, Nikila, you see ln E is 1. So I take the power and I bring it in front. So you'll get the power by 1. And now just to make x is subject to the formula. Right, so just to make x is subject to the formula, x is equal to ln 0.01 over minus 0.3. How much is that? That'll be in centimeters, right?
1.5.
How much? 15.35 centimeters. So I think sufficient here something already. Right, to be sure the same thing, 13.4, 15.4. Right? So in this question, they didn't give you I naught. So of course, you had to figure out how to cancel it out, right? So look at how you come up with So why didn't you see that? No. I was just negotiating. Let's go again. Next one. What's this here?
All right,
What's the answer, yes? No, this one. Huh? This one is Nikila. Which one you have? The answer is what? Dog, right? Next one. Try this one. Wait, some missing here.
No, I had 50 kilos, we need.
Yeah, this is time.
We'll give you that time, sir?
I mean, it is the current. Hey, what did we it does do? What did you?
We also will all do much more. Very good, even I feel, you see. I'll be up by.
That fast? That fast then. Remember, she asked you on it. Huh? Part two. Right, look what they give you up there, right? They give you power. Sorry, they give you voltage and current, so they can find power, right? So you gotta figure out how to get speed.
What do you time they give velocity? You know what we don't time from there?
No, no time.
So that's easy for them.
Ah, I said they want to do me, it's not good. I show you this last, I show you this a little while ago. How you can take it, and you can take it voltage and find energy.
Yeah.
And if you know energy, and you can find.
Let's speed of light.
Huh? It's like
Experience, and it's here now.
it's electrons, but sorry, electrons here.
With the speed of the electron.
That's why you have to move forward.
Oh. But that's speed of the electron will be the same thing forever.
No, if you have energy that the electrons moving with, how you would find the speed?
Directly, yeah.
What the formula you use is equal to what?
It's C.
Oh, you don't know what is C is speed of light.
Oh, wait, I have it here.
It's the electron.
Is equal to QB, no. And I give you that formula.
I will give it that formula. E is equal to half mv squared.
Well, I like the energy.
Right.
Yes.
Well, how is you get the energy of the electron? The energy of the electrons and find the thing. And then find the cutoff wavelength of the X. Every Friday we'll break for.
That 1.6, no, that 9.91. Mass 9.91.
Yeah, just waiting this one. Do it next. We have missed. No, what, who's that? Asa may wala. Asa ko man. Oh yeah, no, share. Yeah, just ask na siya ko man. But she give less.
I've been actually we are really to buy a different school. Yeah.
What is it? Asa ko man. He just asks her, just to her, that's 4 days or 5 days or 3 days or 5, what she wants to do. Or another son, now what he's doing is own.
So it's outside that.
Huh? Right, power is equal to I by V. So that's 1.2 by 10 to the minus 3 by 50 by 10 to the 3. How much you all got there? What you all got for the power? 60 what? Part 2, you're using E is equal to half mv squared. But to find the energy, we are using charge of an electron by the voltage. Okay, and then we arrange the formula and square root it, and you'll get velocity. Sorry, that's lowercase v, right?
The mass of the electron is 9.91 by 10 to the power. So it's 61. Yeah, 61.
What's the mass again? The mass of the electron is 9.11, right?
9.11, 9.9.
What's the mass of the electron again? It's second thing. Plug it in, tell me where you get to the speed. If you get something more than the speed, I do something wrong, right? 1.34 by 10 to the 8. That's good. And what are you using to find the wavelength?
Easy for the initial number.
Nice. And what are you using for C? No, sir. So what are you using for C?
The speed we just now get 1.34.
No, that speed that you found, that's not what the speed of the electron. Right, remember X3 is part of the EM spectrum, right?
It's clear light.
So the speed of light. So you're using 6.63 by 10 to the minus 34 by 3 by 10 to the all over lambda. The lambda was 10 to the minus 11. Right?
No, we have 5 for lambda.
Oh, sorry. But that's what from before.
Easy
Sorry.
for the 60. We do he's not 60. Easy for the speed by 10 to 1. Here, later in that, I have a so here.
Should be close to minus 11, right? Somewhere around there, right? What you got? 2.49 by 10 to the minus 11. So once I get around minus 11, one thing around there, you know, you do the right thing, right?
You get to that, then you get the board.
Yeah, do it, right? Fast and finish.
So you think kind of thing happens.
But it's nice thing to sit down and think.
Very real nice.
You see, what he paying you for, you see something that you didn't before. Because you don't know what come here randomly selection things. It's just way to understand. I didn't do nothing special yet. I just followed the prayer. Huh?
Yeah.
No, but
Yeah,
I see it already.
I don't want to. See, it's not much. And see, you see what we go with that? Nothing is that?
Yeah, so how to come on back. I just okay, but like when I use too much prompts, it had to slow down in the end.
Did you tell them everything?
I told him that later on. I said, but the picture I sent was purely you said, yeah. No, as well argue with some time or no? Right, next one, last one on here.
Hey, what's that? I'm proud of you. You think those actually look at it better than these sort of.
Which one?
All.
Have you done it before?
Nobody, but you want to make it laughing.
No, those are just the first three I put out.
Yeah.
No, I just playing around with the template.
It was to be real. Yeah, if one to watch.
That's
Yeah,
what I'm
boring.
point. Huh?
Somebody was. No, that was but that can you see? Nobody again. This is one of the
Yeah.
Yeah, like before I used to talk. You used to write. No, you talk.
Oh, yeah, that's clear.
Yeah, you got it. I start waiting. So you know what you should have? Sorry. On social media. All this one, appear.
Yeah, we have somebody, but it's like we had to hire somebody who that very expensive. Somebody very expensive. I was bringing whatever see Chamel. Yeah, you know. No, somebody from down. But this one, no, before, that's not popular.
Yeah, she gets it. Come again.
You know, this is one I'm looking for. I must see him somewhere. I'm trying to get indirect link to them now. But you know, something from right down here, right?
Yeah.
He was right found somewhere there.
If you do it, Juliani, right, sir? Next year, let's take that. You had it. You know?
Yeah, but I can't afford them though.
No, but you develop figure now. Yeah, at least all that.
Alright, next one. Let's try one more, right? There's one in our recent year. Oh wait, I think you have a two anyway.
Yeah.
No, I don't know if you put on it. Hold on, I just want to find that's it, see that correct?
Yeah.
So that's not say. But he leave, just the guy leave.
Just because you have your website. Yeah, 1998.
Nah, it's a recent one for sure. That's all they have.
Yeah, but
Alright, so the first part is a label diagram to explain how it's produced, right? Yeah. And then they want to plot a graph. Well, I've got paper.
Yeah.
Then they want to plot a graph, right? After you plot the graph, online, you're seeing, right? It's 2019. After you plot a graph of what? You plot a graph of relative intensity, right, versus thickness. You plot a graph, determine the thickness. What kind of graph it is? A smooth curve, right? And then you got the value. Based on the results, calculate the value. Oh wait, no, we need the graph.
And I last year, he said it was.
Only remember this thing online, eh? Alright, so no, we need the graph to do this. Alright, so what you gonna use here? We're using here earlier in this part. We need the part on top, but on the time to draw a whole graph. What we using here? Right, so we're using I, the attenuation formula is called that, right? I is equal to I naught e to the minus x, right? But we need the part on top. I is the intensity. All right. I want to leave that out.
That will be 1 and 4. So,
I will just see what else out. Introducing X-rays and B, calculating wavelength, we can do this. All right, but that's for. All right, so 2019 is a graph, you did a whole one.
and do it, you know, you want to do it? Hey,
What's this here? So what we're using here to find the wavelength. I can think that all you say whole class, right?
Yeah,
The energy, right? But we had to convert to what first? The joules, right? Right, they already give you energy, so you convert to joules. No, let it plot it. I don't want the other. Then the rest of them will plot it. Right, it came one more time, but hold on, let me try to find it here. All right, now there's that pivot. All right. So we can stop there for today. Right, try 20.